a sum of everything in blue is what we're paying 6.75 cents per kilowatt hour on. And as you can see there, that's roughly, we'll just round up and say $4,000 of that $7,300 monthly bill. So what we're really focused on in this study is looking at ways that we can reduce our peak demand charges. And so that's what we start to talk about here, represented in blue. So this blue box is looking at both our transmission and distribution. So a lot of times referred to as your delivery cost. Um, and that's based on the facility's peak demand. So if we look at that same chart, instead of being concerned about a sum of everything that's in blue, which would be our energy, we're focused on that peak power demand. And so kind of see that arrow pointing to, this instance here. And so this chart is looking at a 15-minute rolling demand window through the month of July. And so this point here where this arrow's indicating that's the 15 minutes where there was the highest demand draw on that farm. And so at that point, your transmission and distribution fees are calculated based on that. And so if you were to combine, a lot of times demand charges are kind of lumped together. If you kind of look at your distribution and transmission demand combined, we're right around $20 per kW now in Ohio. And so, another way to look at this that I think is maybe a little bit more impactful is if you look at the total here, so we'll just say roughly $2,400 of that bill is based on a 15-minute spike in usage. And so that's where the conversation becomes a little bit less about energy efficiency. Certainly, efficiency plays a role in that, but also a big part of that is behavior. And so, thinking about some of the decisions and how we set up controllers, how and when we're running certain equipment that could be run on timers at a different time, those things all going to play into this demand charge. So moving to the last category on this bill, this is one that's probably the most complex to follow along with, and honestly, it's one that for a long time has kind of been overlooked, but it's had a lot of interest here lately, and that's your capacity cost. So a capacity cost, before we kind of jump into that, we have to understand where it's coming from. And so this is a map that is showing the footprint of the PJM interconnection territory. So PJM is Ohio's regional transmission operator. They're operating under federal rule through the Federal Energy Regulatory Commission. And you can see it covers basically it's parts are all of 13 state region. There's 21 different transmission operators in that PJM territory. You can see those that you're very familiar with in Ohio. You have Ohio Edison and AEP and Dayton and Duke, Ohio Valley Electric Cooperatives here in green. So it kind of gives you a sense of who some of those transmission players are in Ohio. But PJM as a regional transmission operator does not own infrastructure. They don't own generation assets or transmission assets. Their role is to make sure that we're maintaining safety and reliability, and then looking at future planning to meet those reliability needs. So we always need to make sure that generation is available to meet the load demand. To do that, PJM's always looking at forecasts that are into the future. And each spring, they do a capacity auction. So if you look at this formula on the bottom here, your capacity costs are based on your peak load contribution and the PJM auction price. So that PJM auction, which I have a slide here to show, is represented in this chart. That's done each spring. And what they're doing is they are sending price signals to generation that is to take place 3 years into the future. And so, you know, those signals are based on a number of things. So, if we have generator assets that are retiring, whether that's due to age or whether that's due to emission standards. The other thing that impacts this is obviously load profile. So right now there's a lot of discussion around data centers and increased load demand. So both of those factors are going to impact these auction prices. So to try and close the circle on this capacity charge. If we think about the your PLC, your peak load contribution, that's based on PJM's five highest load hour intervals over the summer. And so, and that's kind of a key point. They're focused on June 1st through September 30th, those summer hours, which when we think about what's happening in the summer with ventilation, on dairy sites, we have a lot of loads for ventilation where we're running a lot of fans. Um, but when PJM identifies those five highest peak hours, they then take your meter data for those 5 hours and they average it out. And so in this example, 104 kW on that farm was the average during those five highest system-wide load hours on PJM. And then they simply do the math. So that peak load contribution times your PJM capacity price, which is represented in megawatts per day, times 365 days a year. This would be the farm's annual capacity obligation. And then each utility is going to apply that differently. Some of them will do it based on the days in the billing period. Some of them will just break it out monthly and divide it by 12. But you can see that 854 is really close to what was represented on that bill, that consumer. Looking at that from an annual perspective, it really kind of shows the impact of those capacity auction prices jumping from, you can see in dark blue here, was right around $100 per month. And all of a sudden, that bill jumped up to $845 to $850 per month. And that is in a sense, it's a fixed price once they calculate it for the course of that year, that capacity obligation. But again, one of the points is we look at this breakdown and we think about, everything in light blue is kilowatt hours. So that's our energy. So when we think about energy efficiency, that's really going to impact that. Everything else, everything in orange, light orange, and dark blue, I mean, that's really based off of that peak demand. So that spike in usage that is not only going to be impacted by the efficiency of that equipment, but also the behavior of how and when we're operating it. So we have some advanced electric meters on these farms that allows us to monitor each of the critical motor loads. This is an example from July on that farm, and you could see initially we were monitoring all of these critical loads. This gray bar, or gray line at the top is the farm's overall load profile, so everything kind of combined. And you could see this peak that we had here on the 15th. Now, our meters allow us to track our ventilation fan loads, vacuum pump motor loads, cooler compressor motor loads, feed and water activity, and then the manure pump. And before we jump into the ventilation, just kind of a quick illustration again of thinking about holistically how the farm can operate a lot of these critical motor loads and how that can impact your electric bill. Um, you know, we found that this farm's manure pump was running when the ventilation fans were running on because they would come in at the first milking and flip it on manually. And what we suggested was moving that to a window between 3 and 5 a.m. when the ventilation fans were typically off. And, in doing so, just from a demand standpoint, it reduced their demand, right around 25 kW per month. And you could see at $15 per kW, that was an annual savings of just under $4,500. And then as those demand costs increased, since they've made those corrections, you're going to see an even larger benefit from that. So one of the things to kind of keep in mind is as we think about energy bills, it's think about large motor loads and then also whether they're essential or non-essential as they're running. So, Chris, did you want to talk a little bit about the setup of the project, and then we'll jump into some of the ventilation data?
Sure. Yeah, appreciate it. Good afternoon. A little background on this farm. That picture you see there is one of the freestall barns that we're working. It's actually the original freestall barn. It's a dairy farm in East Central Ohio, very high producing herd, about 300 cows. And the original barn, when it was constructed, was basically constructed into a hill, and so there were some ventilation concerns and challenges. They were actually going against the prevailing winds, but given the topography and layout, that was the situation they were dealt. And so over time, they did build another freestall. You'll see an aerial photo of that later on, but did build another freestall. And in the middle of that was the holding pen. And so we had airflow that was kind of pushing against one another. And as Eric mentioned, we do have several years history of baseline data based on some energy consumption information we've collected. So that helped to kind of set the stage for this project. As I mentioned, we had that really a good relationship with them for the on-farm research projects that we had been conducting. And when we looked at some of the data from that and showed some of the results, and then this grant opportunity came along, it kind of made sense to put those two together. And as we looked at that data, we were confident that we could make some recommendations that would save the farm money. And we've seen some of that already. So we did apply for and were successful in achieving a grant through the NRCS, Natural Resources Conservation Service. It's a SIG, Conservation Innovation Grant. And that's the title of the grant. And so we did purchase fans. So the picture on the left is just a section of the barn. You can see the old box fans and the round fans on the right there. Those box fans were replaced with those that you see on the right. And then we kept the other fans, those round fans on the right, and just changed the direction of those so we weren't fighting against the airflow coming from the other freestall barn.
Yeah, so and we'll talk about this in a little bit more detail, Chris, but just so these white fans that my cursor's hovering over, these 36-inch mega flows, those fans were kept, and as Chris mentioned, would just change the direction, as you can see from that image to this image, to go with the prevailing winds. Um, these older box fans up top, these 48-inch box fans, and then five of these cage fans on top of the feed alley. Total, we replaced 12 of the 48-inch box fans and five of those cage fans with 15 of the new stir fans that you can see there. Anything else on that, Chris?
No, we can go ahead and jump on to the next one.
So with that, I think Jordan's going to jump in and talk a little bit about the trade-offs with EC motors.
Yep. So one of the objectives of the project is to install these electronically commutated motors driven fan. And what that means for our purposes is essentially that we can turn these fans down, ramp them down to around 20% of their total capacity, or anywhere in between 20 and 100%. So it's not just a single stage fan that's going to bang on or off because of the signal from the thermostat. We can actually modulate this down to exactly what we need. And there's some big energy advantages there. This is kind of real quick, talk about fan theory here. I promise I won't take too long on the math. Basically says if we're to turn our fan down by half, the rotational speed by half, we would expect to get half of the airflow. That makes a pretty good sense. But if we were to turn the same fan down by half, we would expect not a half reduction in power, but more something like 1/2 to the power of 3, as you see here, which would be 7/8 reduction in power theoretically, or we'd use 1/8 of the power if we're to run at half speed. So there's big energy advantages from turning down these fans a little bit, and we've looked at different ways, and we've done a lot of modeling to see what kind of advantages we get both from an energy perspective and on the peak demand reduction that Eric was talking about. Leveraging that. So you can go to the next one, Eric. So to put that in perspective, let's say we have a fan that at full capacity uses 10 kilowatts to move 10,000 CFM of air. For a single stage, if really we only need a half duty cycle there to be for comfort concerns on a given day, we could turn this on and off and only run it half of the time and be running, let's say, for half of an hour, and that would end up using 5 kilowatt hours just from turning it on and off. For the ECM fan, in contrast, if we were to modulate this down to run the entire hour at half speed, theoretically, this would only take 1.25 kilowatt hours because of that fan law advantage that we're expecting. Again, that's theoretically. We don't get as much as theory predicts in the real world. You can go to the next one, Eric. This is some real data from some similar fans. These are actually from the hog barn, but we measured the relationship between the flow and the power draw. And we aren't getting quite that exponent of 3. You can see we're getting exponent more like 1.9 or 2.4, but this is still a huge advantage. It's still more than linear, so we get more than half the reduction in the power draw for a 50% reduction in airflow. Couple different ways to leverage that. I'm going to talk a little bit later about some strategies we're looking at. We can go to the next slide. One thing to kind of that we realize something we need to look out for. We installed similar kind of fans at this hog barn. On the right is the single stage fans that were running prior to us showing up. I'm sorry, call. And on the left is our fans that we installed. And you can see those red bars are taller than the green bars. And that's because, first of all, we installed more efficient fans, but they also end up moving more air, we found. So we were delivering a better environment, removing more airflow. We're operating these both at full capacity there, but we ended up using more energy there. And what we found is we were actually moving 50% more air with these same fans because they're better at doing what they're supposed to do, which is move air. And then using that scaling from the previous slide, we calculated that if we were to deliver the same amount of air as we were on the right-hand side situation, we'd be doing that for about 4 kilowatts instead of 10, which is what we were operating, or previously we were operating about 7.5 with the old fans. So something to look out for if you get fancy new fans. Make sure you're not providing a better environment unless that's what you want to do. And Jason will talk about that a little bit later. The trade-offs between we have a decision to make now. Are we more concerned with the animal comfort, or are we more concerned with the energy bills? You might be able to, with the same amount of electricity, provide for a better environment, and then you got to make a decision about which is more important to you. You can move on from there.
Yep. And just to kind of wrap that conversation up, Jordan, I think it's important to remember that, we're partnering with private farms, both on the swine or the hog side and also on the dairy side. And so, our initial setup as we're introducing this new equipment into these environments, because they're operating farms, is to kind of set that baseline and have our settings equal to where they were when we replaced that equipment. Get a good baseline, and then looking at this year, so then that second year we'll try to optimize those controller settings to optimize that after we're comfortable with how the barns is in fact cooling. So, a couple slides to just kind of look at some of the preliminary energy data on the dairy site. Again, Chris had the image looking through the barn. Here's kind of an overhead that shows these small circles are those 36-inch mega flows that were there before, and they remained where they were. We just changed the direction. Before we had this West Freestall was moving air from the west to the east to this near the holding pen, and this original main barn was pushing air from the east to the west, and then they had some side fans that were pushing it out. And so as we changed this, everything got flipped around so that we're pushing all of that air now from the west to the east, and we've added 5 rows of 3 with those new Munters EC fans that you'll see here. So when we look at the controller setup, you'll see again that there's 5 rows. So each of those rows has 3 fans. And again, our controller settings initially were fairly conservative. I think we'll look at the data and look to optimize the controller settings moving forward. But essentially, we have four stages, ramping up all 15 fans. So again, we're not necessarily bringing on rows, one, three, and five separately. Everything's coming on at 40% and then slowly ramping up to 60, 80, and then ultimately 100% as needed. Here's a daily snapshot that just kind of helps you visualize that staging of those fans. And so again, each color is representing a fan row of three. So it has three of those fans in each row. And you can see here where it's kind of staging at 40, 60, 80, and 100. And again, we've talked a little bit about both efficiency and behavioral change impacting these, ultimately the peak demand that we're setting. Here's kind of a comparison. The fans that we took out were historically, if you kind of looked at it, a average of their monthly max demand, it was right around 21 kW. And the new fans that we replaced it with were kind of between 15 and 16 kW. So there is a demand savings from those fans just and being more efficient. Taking the staging and the controllers and the settings and all of that aside, the fans themselves are just more efficient at moving air, as Jordan previously indicated. So his theory, I guess we were showing, it was also showing up in our current transformers as we were measuring that load. So I wanted to pull out a couple of monthly load profiles to share, but I think it helps if we kind of take a real step back at a 30,000 foot view on what's happening at this farm in terms of their monthly demand. So again, we're not talking about the overall kilowatt hours, we're talking about the power demand. So measured in a 15-minute window. So what is that highest spike? You can see the over where the farm setting its overall demand, and then in blue is what the ventilation component of that is estimated to be. And so what we see is really March through October. It's pretty consistent where we're setting from a demand component or from a demand perspective, we're kind of maxed out with the need for ventilation that's setting that higher demand. Now, November through February, during those winter months, there does seem to be some opportunities to look at some stuff when there's lower demands for that ventilation. So to look at this, I want to first kind of focus on those summer months, and we'll look at the bookends. We'll look at March and October and see what's happening. So this is looking at the kind of and again, this is the entire month, but the data is a 15-minute rolling window throughout that month. So it's a little bit misleading when we see these spikes. These are essentially these are days where it got warm and there was daily day-long ventilation requirements throughout the month. And you can see, obviously there's a stretch where we had some cool days in March and there was no demand for ventilation. Very similar perspective when we look at October. You can see kind of days where it's warm and we're requiring air movement, and then evenings we're not. Daytime we are, evenings we're not. As you got towards the end of the month, it just kind of cooled down and there was no need for additional ventilation. And then sometimes, right, I guess, so to help you visualize this, so I just picked a day. So this day is actually March 22nd, but I want to kind of help understand those spikes that we're seeing. They're really day-long spikes in ventilation needs. And so you can see here, this is March 22nd. We're looking at a 24-hour window. 9 o'clock, we started to have a need for some ventilation. By 11 o'clock, we're all fans are kind of ramped up at full capacity running. So what you're seeing here is in light blue, this is it's labeled sub panel, but this is essentially ventilation fans in the West Freestall barn. And so there's a small office there. So there's you see some load activity there. That's light office equipment. And then it's staged up where there's two different barns that have ventilation needs. And so you can see here everything in blue. Those freestall barns to the west are running, and then of course the five stages of fans that we put into the original barn We're slowly ramped up, but ultimately running at 100% for most of the day. And then again, just looking at the center or the middle of that kind of that monthly perspective that we were looking at, there's just not a lot of opportunity when you think about controller settings or staging, because it's just there's 100% need for ventilation. Now, again, if you recall that first slide that I showed the staging of those new fans, there was an improvement in efficiency, right? So that main barn, everything that you see here in purple, red, yellow, gray, and green, that barn was requiring about 21 kW to ventilate it, and the new fans were between 15 and 16 kW to ventilate it. So even though everything's running all the time, there is still a savings. We've reduced that demand from just over 50 kW to, our ventilation loads are in the, 45 range now, because those fans are more efficient. But in July, they're just running all the time. Um, Wanted to talk a little bit about November through February, and this is kind of interesting. So I'm just going to show a couple slides specifically focusing on November, but you just have to trust me. I can share some additional slides, at a later date if someone's interested in seeing them, or ultimately I think we'll get some type of a fact sheet. But each of these months we observed the same thing, and that was, initially I was a little bit disappointed that when you looked at November of 2025, the fans that we replaced, the new fans in the original barn were kicking on. They kicked on twice here, you can see in November. So, an unseasonably warm spell where it got warm and those fans kicked on. But, the fans in the Western freestall, those other 29 fans did not kick on. And initially the thought was, well, that's not a good thing if the new fans we're putting in are kicking on and drawing more of a peak than what the old ones were. But talking with the farmer, he said, no, that's a good thing, because historically all of those fans and the other freestalls would kick on, but since he's installed the new fans, they don't. Just the new fans kick on, and it pulls enough air through those it pulls enough air through here that it's causing these fans to not kick on. So, that's where kind of that question mark was, where the farmer's like, no, historically these fans kick on throughout the winter months when we have a little bit of a warm spell. But since we've installed the new ones, they're not. And so it's actually there is quite a bit of a demand reduction there. If you look at this is looking at some of the history here. So in November. They had in November of 2020, you could see in the Western Freestall barn, so these would be the old fans, um, all 29 of those kicked on, and your demand cost was right around $660. Had a similar instance in 2022 where it got warm a couple days in November, and those fans kicked on. What the farmer's suggesting and what we've observed when we looked at the data, because if you look at 2024 and 2025, um, you know, w- while our new fans are kicking on, these fans that we didn't replace are staying off, and there's a lot more of them. So there is a significant demand savings there that we really weren't looking for, and had we not, talked through that with the farmer, might not have recognized. But I do think that there's some opportunity for, if you were to retrofit an entire farm, how you might set those fans up to lower that demand spike on an unseasonably warm day in the winter. And I think Jason will talk about that here in just a minute. A couple of key takeaways. Again, we've replaced 17 fans with 15 new ones. We did see a noticeable reduction of around 6 kW from 21 down to 15 kW in that new barn where we've replaced those fans. And again, that's about $120 per month. So based on your transmission and distribution fees combined. Um, any reduction in demand from more efficient equipment will likely benefit that peak load contribution. So when we think about those increasing capacity costs from PJM, it's a little bit of a roll the dice because it's based on the previous year's 5 peak load hours on the system, and we can't predict those. But if we know that the fans that we've replaced are saving us 6 kW, in that barn each month, then that's going to be an observed savings when it comes to calculating that peak load contribution. And then just one thing that I will note, not going to talk much about it, but you can see the image here. We did have one fan that had a faulty motor drive that we had to swap out. And so that was designed as kind of a plug and play where you can replace it in the field. Could be done, but I will say, talking with Scott, it was a little bit challenging changing that up there, hanging from the rafters. But anyhow, we got that swapped out. So with that, I think Jason or Jordan be talking
Me.
about strategies here.
Yep. So we've been looking in, we've run some simulations of a couple different kinds of barns that we're working on. So look for additional demand savings. So Eric mentioned the big one is just that when we're installing better motors, we would expect that even delivering the same airflow or not changing the way they're operated at all, just running with better motors, we would see something like a 40% reduction in the power draw. Um, and that alone will reduce our not only our energy bills but our demand as well. But we look for some other things, especially kind of considering strategies that are done in other kinds of commercial buildings. Is there any other way that we can operate and modulate these fans up and down in a way that we could reduce that demand charge? So the first conclusion we came to during the summer months, most of the time, the full capacity of the fans is needed, at least at some portion of the day. So that's going to determine the peak load contribution. It's also going to determine that monthly peak that Eric was talking about. So there's not a lot of opportunity just through controls during the summer to reduce that peak, just because at some point you're going to need the full capacity of the fan. And any reduction in that airflow from the fan is probably going to result in a temperature that's unacceptable. So we need to limit these strategies to like shoulder seasons, so talking spring and fall. And then we looked at a few things we thought might be advantageous in those times of the year. So you can go to the next one, Eric. So one thing that we do in commercial buildings, human occupied buildings, sometimes it is what we call pre-cooling. So in the morning, you don't necessarily need as much cooling in the summertime as you would, afternoon when it's nice and hot outside and the buildings had time to warm up. So one strategy for demand shifting in commercial buildings is overcooling in the morning, and the walls and the floor and all the building kind of cools down a little bit, and then we can kind of undercool during the peak time. The peak usually happens late in the afternoon because we've already kind of charged the building. We looked at trying to do that in barns, and we found that it's not really possible. The pre-cooling strategy had very little effect on the temperatures. You can kind of see it here. By the afternoon, we've already caught up, and that kind of pre-cooling effect is already gone. And that's probably because the barns, compared to concrete commercial buildings, are not as massive, not as good at holding things, and they're also very open and leaky. So that strategy was kind of a dead end for us. So we looked at a few other things. We can go to the next one. One thing that might be promising, Eric talked about, if you get another piece of equipment that's coming on simultaneously. I guess we got a few notes there, sorry. That is adding on to the ventilation power draw, and that's determining your peak load contribution or your monthly kind of 15-minute peak. One thing we looked at in the shoulder seasons is, can we just kill the ventilation or reduce the ventilation for the time that that other large piece of equipment needs to run, maybe for an hour. But we saw that that is in most cases possible. If the outdoor temperature is below about 80 degrees Fahrenheit, we can get away with letting the barn float a little bit during that hour. And in that way, reduce our power draw from the ventilation fans by something like 4 kilowatts, and in turn, reduce our peak demand by that same amount. You can keep going. Yep. And I think this is Jason's part where we're talking about the difference between the other trade-off between production and energy concerns.
Yeah, so we can go to the next slide. When we look at everything that's been talked about today, there's some trade-offs, between energy conservation and cow comfort. So it's really looking at some data that's available. This is kind of the next steps for the project on some of this too, where we start making adjustments on farm. But ventilation goals are 60 air changes per hour. And then looking at cow level, we want to maintain a lying down airspeed between 2.5 to 5 miles an hour. And that's one of those areas where when we talk about that, those spikes that we saw in March and the variable speed on those fans, there may be some advantages to running those fans slower, maintaining that minimum airspeed during those warm times in the spring and the fall, and decreasing the total energy demand in those months. And then in the summer, we may want to run those a little bit faster, make sure we don't have any dead spaces in the barn, as especially here in Ohio, when we think about March and October, we do have cool nights. When we pulled out that full days graph, you could see that those fans were shutting off overnight, which would have allowed those cows to cool down and dissipate that heat. But when we think about that, we want to make sure we're maintaining lying time, we maintain dry matter intake and milk yield, and really looking at ventilation beginning when we hit that temperature humidity index of a 68. And if you go back to our fan specs, our fans actually start kicking on at about 60 degrees. There is a need maybe for a low amount of air movement, but not really effective cooling until we hit that 68 degrees, which in this study, those fans were up to full ventilation by that temperature humidity index of 68. So when we look at some work here from Wisconsin through the Dairyland initiatives there, you can see at the maximum daily relative vaginal temperature, when they look at control and then two different fan speeds, 60% power, which was running 2.6 to 4.5 miles an hour, or 100% power, which was running around that 2.5 miles an hour, we see that difference between those fans. The red there is the control, and then black is 60% power, blue's 100% power. And as we follow those lines, we really see that increase in power doesn't have any advantages to cooling and maintaining cow body temperature, vaginal temperature there. Between 60 and 100%, getting that airspeed over that 2.5 mile an hour didn't provide any additional body temperature, vaginal cooling for those cows. You do see kind of out there at that 85 temperature humidity index. It does start to trend lower. So that would need investigated if you're in a southern climate. At that point, you're probably providing evaporative cooling also with sprinkler systems to see if there's any advantage to increased wind speed at those higher temperature humidity indexes. But for temperature, there was not. Next slide. So then when we look at a couple other things they found in that study, continuing with red being your control, black is 60% power, and blue is 100% power. No statistical difference between those two power settings on milk yield when we get up into that 75 to 85% or 85 THI. So running those fans slower, conserving power was maintaining our milk yields. We do start to see in that study, though, a little bit of a trend towards a deviation in dry matter intake, where providing some additional fan speed, when we got up to that 75 or 80 THI, we start to see some separation there in dry matter intake. It's about 0.9 kilogram advantage from above the control for 60%, and about 1.5 kilogram advantage in dry matter intake at that 100%, leading to, if you have that ability, maybe there could be some advantages when we get on those really high THI days to ramping those fans up. But going back to that, how do we conserve energy in the months where we could have a lower energy bill, because those fans aren't running the entire time, so that across the entire farm we're not charged at that higher demand load, especially getting into March and April here in Ohio or the upper Midwest. If we're running those fans a little bit slower, providing that minimum effective cooling when it's needed, there's definitely some possibilities there to save on energy use. Next slide. So when we think about saving on energy use and what we can do, you really need to evaluate your system as you set up these controllers on farm and work with producers to look at what is your fans, especially when you put in these new fans, what are they doing on farm? When you replace a fan with a more efficient fan, maybe we can slow that down. What do we need to look at? Really looking at airspeed, where those cows are lying down. So that yellow bar down there, it would be an example of a freestall row, and the blue is where the fan is at. So we basically want to check every other freestall between fans and make sure we're measuring under each fan to tell us two different things. Are those fans positioned properly, that they're actually moving the air down where the cow is? And do we have that airflow the entire length? And what is that airspeed as we get out further from the fan? Do we maintain effective cooling from where each fan's plume starts and stops? Would recommend, measuring at least 3 fans in a row, measuring every other stall, and then going to some other sections of the barn and checking at least 1 fan to see if you're in a naturally ventilated barn, what those conditions would be. If it's a cross-ventilated barn or tunnel ventilated, it's a little bit of a different layout as to how you're going to check for those, that airflow across the barn, wanting to check under baffles, and then also wanting to check different areas of the barn on that tunnel ventilation to make sure we're maintaining that air down on the cows. Over there on the left is a Kestrel wind speed monitor that can be used to check that. You can use a lot of different options. The thing is, you just need that tripod and air vane so that sits up at the cow's back height when she's laying down, and that air vane gets it corrected to the wind direction throughout the barn. So with that, we wanted to leave a little bit of time for questions. So I think next slide should be closing thoughts and questions.